paper that's been causing quite a stir in physics.
Oh, yeah.
It's called Operationally Classical Simulation of Quantum States. It just came out on February 4th, 2025. And get this. It's about how to simulate quantum states using classical devices.
Wow.
Pretty wild, right? We're going to untangle how these researchers are giving classical a whole new meaning.
Right.
And what that means for the limits of, well, everything. Classical and quantum. But before we go too far, let's recap.
Sure.
Classical versus quantum states. You know, in the classical world, everything is certain, no superpositions alike.
Right, yeah. Everything nice and tidy, existing in a single state. The traditional view of quantum coherence hinges on the basis you're using. It's like looking through different colored glasses.
Okay.
Only the states aligned with those glasses appear classical. But here's the thing. Change the glasses, change the basis, and what was quantum might suddenly seem classical.
It always felt like a bit of a cheat to me.
It does complicate things.
Which brings us to this new paper, right?
Yeah.
They've got this brilliant idea. Operationally classical. No more getting lost in the abstract math. They're focusing on what devices can actually do.
It's a fresh perspective. Imagine a bunch of classical devices, each generating states based on a specific basis. Now, picture randomly choosing which device to use each time.
Okay, so like a bunch of gumball machines, each with a different flavor.
Exactly.
And I'm picking one at random. How does that simulate quantum states?
The magic lies in how these simple devices are combined. This random selection process allows you to simulate certain quantum ensembles, even ones with properties we associate with quantum systems, like non-commutation.
Wait, non-commutation, remind me about that.
Sure. It means the order of operations matters. In the quantum world, measuring a particle's position then its momentum can yield a different result than measuring momentum first. It's classic quantum weirdness.
Oh, right. So these simple classical devices, by combining them this way, can mimic some of that quantum behavior.
They can.
That's amazing.
Yeah.
But what about noise? Doesn't that mess things up in the quantum world?
Noise is definitely a factor. Think of it like static on a radio signal.
Okay.
Introducing uncertainty and disrupting those quantum states. Interestingly, this paper uses noise to its advantage. They introduce isotropic noise. Imagine blurring the output of those classical devices.
So they're adding fuzziness on purpose. Why?
Because adding just the right amount of noise lets you simulate even more quantum states with these classical models.
Really? So noise can help bridge the gap between classical and quantum. That's counterintuitive.
It is. And the paper quantifies exactly how much noise these models can handle.
So there's a breaking point where classical can't keep up with the quantum weirdness.
Exactly. They found a specific noise threshold for each dimension. For qubits, it's like shrinking the block sphere a way to visualize qubit states in half. Anything inside that smaller sphere is classically simulable.
Whoa, so noise is carving out a boundary between the classical and the truly quantum. That's a game changer. But if noise is the key, how do we know we're dealing with genuine quantumness, not just a classical trick?
That's where things get even more interesting.
Okay, I'm hooked. How do we know if something is truly quantum?
The paper talks about these things called witnesses. Think of them as tests.
Ooh, I like tests.
That we can run in the lab. These tests are based on mathematical inequalities that classical models have to follow.
Okay.
But quantum systems, they can break the rules, violate the inequality. That's how we know they're tapping into something truly quantum.
So like a quantum lie detector. If it breaks the inequality, we know it's not faking it. That's so cool.
It is. The paper gives some examples of these witnesses using something called mutually unbiased bases, or MUBs.
MUBs. Are those anything like my old college roommate? He was definitely unbiased.
Not quite. In this case, MUBs are special sets of basis states. Think of them like different lenses giving us different views of the quantum system.
All right.
The more MUBs in our witness test, the more robust it is against noise.
So like adding more lenses to our quantum microscope, we get a clearer picture, even with all the noise.
Exactly.
But we've been talking a lot about simulating single system states. What about when we scale things up, those spooky entangled particles that Einstein hated?
That's the big question. Remember how the paper found that noise threshold? Well, as the system grows, the noise tolerance of classical models plummets. This suggests that higher dimensional systems, especially those with entanglement, might be where the true power of quantumness comes in.
Hold on. Entanglement. I always struggle with that one. ELI 5.
Sure. Imagine two coins flipped at the same time. No matter how far apart they are, if one is heads, the other is tails, right? It's kind of like entanglement, but way weirder. With entangled particles, they haven't decided their outcome beforehand. They're in this fuzzy state until we measure one. Then, boom, the other one instantly knows what to be, even if they're miles apart.
That is spooky.
Yeah.
No wonder Einstein had nightmares about it.
Yeah.
But how does this operationally classical stuff apply to entangled systems?
That's one of the big open questions the paper leaves us with.
Really?
They focused on single system states, but extending these ideas to entangled systems is a whole new challenge. It could be that classical models struggle even more there.
So the more entangled things get, the less classical they become. Entanglement is a measure of how much a system is breaking free from the classical world.
That's a great way to put it. And that has huge implications for quantum computing.
Okay.
Imagine simulating a complex entangled system with millions of particles on a classical computer.
Yeah.
It would be impossible.
Ouch, my brain hurts just thinking about that. So knowing where classical models break down is essential if we want to build powerful quantum computers that can solve those impossible problems.
Exactly. It also helps us pinpoint the types of problems where quantum computers will excel. It's like knowing the enemy's weaknesses.
Interesting.
You can target them strategically.
Right. So understanding these operationally classical models gives us a roadmap to the quantum future.
Yes.
We're seeing the boundaries when classical ends and quantum begins. But let's zoom out for a second. Why should someone who's not a physicist care about any of this? What's the big takeaway?
It challenges our understanding of reality. It suggests that the boundary between classical and quantum is blurrier than we thought. What's more, it has practical implications. Understanding the limits of classical models can help us design better quantum technologies.
So not just theoretical stuff.
Absolutely. Think of quantum cryptography. We want to use those spooky quantum correlations to send information securely.
Right.
But knowing how much noise those correlations can tolerate is crucial for designing practical quantum communication systems.
It's like we're learning the language of the quantum world, understanding its rules. But this paper is saying those rules aren't as rigid as we thought.
That's right.
And that there are ways to bridge the gap between classical and quantum.
It's making me wonder, could we use those classical models to, say, design quantum algorithms or simulate new quantum materials?
That's a great question, and it's an area of active research. The paper hints at some exciting possibilities, but there's one more key takeaway.
Okay, what's that?
This idea of quantumness as a resource.
Interesting.
You see, traditionally, noise is seen as the enemy of quantum systems.
Right, noise disrupts those delicate quantum states.
Exactly. But this paper flips that script.
Oh, how so?
It suggests that by identifying those noise thresholds where classical models fail, we're mapping out the regions where quantumness is truly essential. It's in those noisy regions where we find the most interesting quantum phenomena.
Wait, so noise can be a good thing, like it's a signpost pointing us towards the most valuable quantum resources. Exactly. Noise highlights the regions where the quantum world is truly unique and powerful. And that's a profound shift in perspective.
I see.
It means we need to start thinking about noise not as something to eliminate, but as something to understand and potentially even harness.
Okay, my mind is officially blown. So we're not just trying to simulate quantum states with classical models.
No.
We're also using those models to figure out where the real quantum magic happens, where the classical world just can't keep up. That's a whole new way of looking at things. So we're not just trying to simulate quantum states with classical models.
Right.
We're also using those models to figure out where the real quantum magic happens.
Yeah.
Where the classical world just can't keep up. That's a whole new way of looking at things.
It is, and it could change how we approach quantum technologies completely. Like, instead of always trying to get rid of noise in systems, maybe we should be looking at how to use it to our advantage.
Interesting.
Maybe we can make quantum algorithms that work well even with noise, or even use noise to make certain quantum effects stronger.
So it's like turning the enemy into a friend, using the power of noise to make quantum tech even better. That's incredible.
It is. And this paper is just the beginning. There's still so much to explore.
I bet.
What happens when we try these ideas with more complex systems? Can we come up with even better witnesses to find those areas of true quantumness? The possibilities are endless.
It feels like we're just starting to explore this huge unknown world.
Yeah.
And this paper gave us a sneak peek of what's out there.
Yeah.
But I have one last question.
Okay.
For someone listening who's not a physicist, What's the one thing they should remember from all of this?
The quantum world is full of surprises.
Definitely.
And the line between what's classical and what's quantum is not as clear as we used to think.
Right.
Understanding where classical models stop working is really important for unlocking the power of quantum technologies.
I agree.
And maybe the most important thing is we need to start thinking about noise differently.
How so?
Not as the enemy, but as a possible tool to help us use the quantum world.
That's a really great point. So to everyone listening,
Yes.
keep thinking, stay curious, and remember, the quantum future is full of amazing things. Thanks for joining us on this awesome deep dive into the quantum world.